Okay, so let's get started here. So this is going to be the first video on radicals. So this set of notes is called Radicals are Exponents. So what do I mean by that? So the way that these notes are broken up is they're broken up into 3 different sections, and then we have some sample problems on the back. So we have rational exponents as our first heading. And our first sample problem is going to be x to the 1/2. Now you might be thinking, wait, how can an exponent be a fraction? How can an exponent be a fraction? Right? We know what x squared means, right? X squared is x times itself, x cubed is x times x times x, x to the 4th is x times x times x times x, and in general, an exponent just means, oh, that's the number of times something is being multiplied by itself. But we have a fraction here. Now, what this means is it's really the inverse of what we would think of with exponents. And so we have an expression that gives us a radical. A fractional exponent or a rational exponent is the same thing as a radical expression. So in this case, we have x to the 1/2, which is equal to the square root of x. These are equivalent. Next one is x to the 1/3, and this is equal to the cube root of x. Now, real quick, one thing about writing radicals, when I write radicals, I want to be very careful because, and this is what I used to do in Algebra 2, you want to make sure that the index of the radical, which is this little number here, in this case it's a 3, is in its proper place and not in front of the radical. So make sure that this is where it's supposed to be and not in front of the radical. Now, a lot of times I would extend the little v part of the radical sign just so that I could nest the little number, nest the index where it's supposed to go. All right, the next one is x to the 2/3. Now, the denominator of the rational exponent determines what the index of the radical is. So in this case, we have a cube root because the denominator of the fraction is 3. The denominator of the fraction is 3, so that determines the index of the radical. Now this 2 on the top, this 2 in the numerator, determines the exponent on what's underneath. So instead of it just being the cube root of x, we have the cube root of x squared, because it's x to the 2/3 instead of x to the 1/3. All right, this can also be written another way. This can also be written as the cube root of x, all raised to the 2nd power. These are one and the same. Now, the reason why I stress that these are one and the same is because there are instances where we want to write it like this, with the exponent underneath, and there are instances where we want to write it like this, with the exponent outside. Next is x to the 4/5. Now, again, when rewriting these exponential forms as radical forms, it's very important that we come up with the index first. We have to figure out what is the index of the radical that we're looking for. And again, that's given by the denominator of the rational exponent. So the denominator is 5, so my index is also going to be 5, and I'm going to work with a 5th root. Now, a 5th root doesn't really have a special name. Like, this one has an index of 3, this radical has an index of 3, so we call it a cube root. But we don't really have fancy names for any radicals with an index higher than 3. So anything higher than 3 is just a 4th root, 5th root, 6th root, 7th root, etc. In this case, the index is 5, so we have a 5th root here. Now what goes underneath? Well, the variable is x, and the exponent is the numerator on the rational exponent, so that's going to be a 4. This is one way to write it, where the exponent is underneath the radical. The other way to write it is where the exponent is outside of the radical. And again, our index is 5 because the denominator of the rational exponent is 5. Again, this is a 5. All right? And the variable is alone just like that. So again, we have 2 ways to write this. We can write it one way where the exponent is underneath the radical and one way where the exponent is outside of the radical. These are both interchangeable. They both mean the same thing. Same with this. All 3 of these mean the exact same thing. All right. Next, let's go to 2 variables. So we have x to the 3/7 times y to the 2/5. Now, when we have 2 rational exponents like this, when we have two rational exponents like this, we have to treat these as two separate radicals. So for example, this first expression is x to the 3/7, so we're going to evaluate this one separately, or not necessarily evaluate. We're going to rewrite this one separately from the y to the 2/5. So we're going to rewrite x to the 3/7, and then we're going to rewrite y to the 2/5. So we have x to the 3/7. The way to write this, and again, if you want to jump ahead and write this in radical form first before I do it, that's fine. X to the 3/7. Think about what number would go here in the index. What is the index? Take a moment to think. Using what we've learned, and again, rewind the video if you have to, what is the index? If you have no idea, you need to rewind the video, because I want everybody to be able to guess what goes here for x to the 3/7. Again, x to the 3/7, we're just looking at this part right now. What goes here in the index? Okay, it should be a 7, because the denominator of the rational exponent is 7. And we have x to the 3rd here. And then we have the radical form of y to the 2/5. Again, take a moment to think. What is the index that goes here? Again, we're just working with y to the 2/5 now. We're writing that in radical form. All right, should be 5, and then y squared. Now we can write these, we can write both of these in the form where the exponent is on the outside. That's fine. We can do that. What we can't do, however, is write these under a single radical. So oftentimes you can write expressions like this under a single radical, but if we were to try, if we were to try to write these under a single radical, we'd have a bit of a problem, because these two radicals have different indices, which is the plural of index. These two radicals have two different indices. One is a 7 and one is a 5. So because of that, we can't actually put these under a single radical, unfortunately. So we're going to leave it like this. The last one, which I want you to take a moment to try on your own, is x to the 4th, y to the 3rd, all of it raised to the 1/5. So pause the video, take a moment to try to rewrite this expression in radical form. And there are two ways to do it. Okay, so I'm going to do this the long way. So the long way is, since these are both exponents, and we have an exponent on the outside, we can distribute this exponent and make this into x to the 4/5, y to the 3/5. All right. Now, keep in mind, I'm doing this the long way. If you get the same answer as me at the end, then don't change anything. So watch me before making any changes, because you may have gotten the answer right even if you didn't do it this way. All right. Now from here, we can rewrite these in radical form, where we have the 5th root of x to the 4th times the 5th root of y to the 3rd. Now, because these radicals have the same index, we can write them together. And again, this is why, if you were able to jump from here to what I'm about to write, then don't change anything, because that works too. That's the other way to do it. So we have a 5th root of x to the 4th, y to the 3rd. And again, if you were able to see that all of this goes under a 5th root, and you just jump straight here, that is the second way to do it. That is the second way to do it. So please don't change anything if you didn't do these two steps and you just went straight from here to here. That's perfectly correct. All right, I have to pull up the rest of these. Okay, so now I'm going to scoot this paper up, and we're going to write next to the problems that we just did. We're going to start with 4 to the 1/2. Now let's rewrite this in a radical form first. So our index is going to be 2, but do we have to write the 2? No, we don't. 2 as the index means that this is a square root. So by default, if we don't include anything in the index, that means it's a square root. So we don't have to include the 2. but we do have to include the 4 underneath because that's what's being raised to the 1/2 power. So something raised to the 1/2 power is the same as the square root. So we have the square root of 4. Well, wait, the square root of 4 is just 2. Yes, it is. That is the answer. So 4 to the 1/2 is equal to 2. All right, the next one is 216 to the power of 2/3. 216 to the power of 2/3. Now let's rewrite this in radical form first. So take a moment, and I want you to rewrite this expression in radical form first. Okay, so what is the index of the radical? Well, it's the denominator of the exponent. So that's going to be a 3, making this a cube root. And what's left over? Well, we could write it one of two ways. We could write it with the exponent on the outside, or we could write it with the exponent on the inside. If we write it with the exponent on the inside, then we would be left with 216 squared. All right? Now, here's the issue with that. If I were to write this as 216 squared, and I would like to have a pencil for this, but I don't see one. If I were to write this as 216 squared, then I would have to square 216 and take the cube root of that, leading to an enormous factor tree. And let's not do that. Okay. So let's rewrite this as the cube root of 216, all of it squared, like that. We know that these two are equivalent, but now we have the cube root of 216, and 216 is a perfect cube, as you should remember from Algebra 1, or if you don't, it's fine. But this is something that is covered in Algebra 1, so the cube root of 216 is 6. But is this just 6? No. The cube root of 216 is 6, but we're squaring it, so this is 6 squared, giving us a grand total of 36 for 216th to the 2/3 power. All right, the next one is 128 to the power of 1/3. Now let's rewrite this in radical form first. So we're going to write a what type of radical? Should be a cube root, because the denominator of the exponent is 3, so the index of the radical must be 3. Underneath goes 128. All right, 128 is not a perfect cube, so we're going to have to break it down. We're going to do that, let's say, over here. All right, so 128 breaks down into, let's see, 64 and 2. And again, you can break this down however you would like. This is one way to break it down. If you find a better way to break it down, or if you find a different way to break it down, you'll still get the same answer. 64 breaks down into 8 and 8. Oh yeah, something that's important is that we're looking for a cube root this time. That's kind of important. You'll see why in a second. So this is 4 times 2. This is 4 times 2. 2 times 2. 2 times 2. Now we should be left with 1, 2, 3, 4, 5, 6, 7 2's, which makes sense because this is 2 to the 7th power. Anyway, because we're looking for a cube root, normally we would find pairs, right? If we're breaking down a square root, we learned this last unit. If we're breaking down a square root, we would find pairs that go together. This time we're looking for groups of 3. So we have one group of 3, we have 2 groups of 3, and we have this 2 left over. So, again, we're looking for groups of 3 because the index is 3. If we were dealing with a 5th root, we would be looking for groups of 5. If we were looking for a 6th root, we would be looking for groups of 6. Now, because we're looking for a cube root, we're looking for all the groups of 3. So, because we have 2 groups of 3 2's, we're going to pull out a 2 for this group of 2's, times a 2 for this group of 2's, times the cube root of whatever's left. In this case, that's a single 2. Now, if you're wondering why we pulled out a 2 and not an 8, 2 times 2 times 2 is 8, and the cube root of 8 is regular 2. So now, outside of the radical, we have a 2 for the group of 2's, times a 2 for this group of 2's, times the cube root of whatever's left. So we end up with 4 cube roots of 2. And that is the simplest radical form of this, of the cube root of 128. Alright, I'm going to warn you, you can put this into Desmos, you'll get a decimal. If you put the decimal, you'll get no credit. Please put this in radical form. Alright, though you probably already figured that. Alright, 243 to the 3/5. I want you to take a moment to solve that on your own. Okay. Oof. Sorry. So, we can write this as the 5th root of 243, all of it cubed, which gives us 3 cubed, which gives us 27. Again, I wanted you to do this on your own, so hopefully you took a moment to pause the video and do this on your own. If you didn't, then I don't know. Yeah. Please follow my instructions next time. Okay. That will do it for this section. So now, let's move on to variable radicands. Okay, let's scoot this paper down. Variable radicands. Here we have x to the 5/3. Now, this, we've dealt with variable radicands already, right, with these examples here, but this time we have an improper fraction. So, keep in mind that we can write this as the cube root of x times x times x times x times x, right? We know that this is the cube root of x to the 5th, right? We can write this in radical form just fine. This is the cube root of x to the 5th. And now, since it's a cube root, we're going to pull out a group of 3's. We're going to pull out groups of 3. So, we have a group of 3 x's and 2 left over. So, we end up with x times the cube root of x squared. Because x represents this group of 3 x's here, and the x squared represents the 2 x's left over. Let's do another one. Okay, x to the 7th, y to the 6th, all raised to the 1/5. Alright, so this is going to be the 5th root of, well, we can think of it in 2 ways. We can think of it as the 5th root of x to the 7th, y to the 6th. We can also think of this as 2 separate radicals, right? The 5th root of x to the 7th times the 5th root of y to the 6th. Alright, and I do want us to get into the habit of breaking these apart, because when we get to the next problem, actually, we're going to have to break this apart a lot. Okay, so let's think about this separately. X to the 7th is underneath. We have the 5th root of it, which means we're looking for groups of 5. If we have 7 x's, how many groups of 5 are there? There should be 1 group of 5, right? Because this is 7 x's written out in multiplication. So 7 x's written out in multiplication, and we're looking for groups of 5. That's going to be 1 group of 5 x's. And how many are going to be left over? 2 of them. So there's 1 group of 5 and 2 left over. Y to the 6th, that's 1 group of 5 y's and 1 left over. Because there's 6 y's, we can take 1 group of 5 out from under the radical, and we're left with 1 left over. So, we're not actually done here. We can write everything on the outside together, and everything on the inside together. Just like that. Alright, for the last one, I want you to take a moment to figure this out on your own, but I am going to give you a head start. Alright, 256, x to the 8th, y to the 10th, all raised to the 1/3. We're going to split this up. We've got the cube root, right? And if you don't know why this is a cube root by now, you need to rewind the video. Don't go any further if you don't know why this is a cube root. Okay, 256. is under here. Cube root of x to the 8th. And the cube root of y to the 10th. We split this up into 3 parts, and we're going to deal with each one separately, and then put all of our answers together at the end. So, the cube root of 256, you're going to do that first. The cube root of x to the 8th, you're going to do that second. And then the cube root of y to the 10th, you're going to do that third. So everybody pause the video now, and this should probably take around 7 or 8 minutes for you to do. And I want everyone to do that. Everyone who's watching this, do that real quick. Take 7 or 8 minutes to do this problem out. Alright, if you have not finished, please pause the video and finish. Okay. The cube root of 256. When we break this down, it should give us 2 times 2 on the outside, right? So when we break down 256, it should give us 2 times 2 on the outside and 2 times 2 on the inside. So that's 4 cube roots of 4. The cube root of x to the 8th, well, there are 2 groups of 3 x's and 2 x's left over. So that's going to be x squared on the outside, and then x squared on the inside, because there's 2 groups of x's that we can pull out and 2 left over. And then we've got 3 groups of y's that we can pull out and 1 left over. So that's going to be, that's a cube root as well. So that's going to leave us with 4x squared y cubed times the cube root of 4x squared y. Okay. That's going to do it for this section. We're going to move on to some caveats. So there is, if you don't know what the word caveat means, there are some nuances to these properties. There are a couple of nuances to these properties. All right, now, unfortunately, yeah, there are some nuances to this. The first one that we're going to look at is x to the 3 halves. And this does not behave as it normally should. So we can do this out normally. Everybody take a moment and write what this would normally be in radical form. So actually do this out. So we should get the square root of x times x times x, and we have 1 group of x's to pull out and 1 left over, so that should give us x square root of x. However, this is a very, very specific case. If we were to plug in a number that is negative, it would cause this to go imaginary. And so because of this, this actually doesn't hold. Going from the square root of x cubed to x square root of x does not always hold when the variable is negative. And so you don't actually have to know this for the test at the end of this unit. You don't actually have to know this for the test at the end of this unit. But if you are planning to go to pre-calculus at any point, including college, you're going to need to know that this produces an absolute value on the outside. And that's just to account for the irregularities that happen when you pull something out of a radical that has an even index. So if you're pulling something out of a radical that has an even index, it's going to have absolute value bars sometimes. It's going to have absolute value bars if it needs them. Let's put it that way. If it needs them, what you pull out from under the radical is going to have absolute value bars. Now let's look at a case where something doesn't need absolute value bars. So here we have y to the 5 halves. So here we have the square root of y to the 5th, right? And here we have 2 groups of y's that we can pull out. So that's going to give us y squared on the outside with 1 left over. Now here's the thing. Y squared, even if y is a negative number, y squared cannot give us a negative number, because a negative times a negative will give us a positive number. So no matter what, y squared will be positive. And therefore, absolute value bars here are redundant, because this y squared will always give us a positive value anyway. So this doesn't need absolute value bars because it's already always positive. Whereas the x did need absolute value bars because it can be negative. Okay. So yeah, I'm going to put here, this is positive anyway, so no absolute value bars. Alright, next we have 5x to the 5 halves is our next one. Now here's the thing, alright? When we write this, and we have a monomial term here, and the exponent isn't 1. The exponent that's going to be underneath isn't 1. We need to be very careful, because this is going to be the square root of 5x to the 5th. Okay, now because all of it is being raised to the 5th power, we have to be very careful. We could do 5 to the 5th and write that all out and then take the square root of that. That's really, really long though. Let's do this instead. So we've got 5 to the 5th times x to the 5th, and we're going to leave that 5 to the 5th like it is. The reason why we're going to leave that 5 to the 5th like it is because it's going to save us some time. So let's split this up. We have the square root of 5 to the 5th times the square root of x to the 5th. Now, just like we did with y to the 5th under a square root, we know that there are going to be two groups of 5 that can be pulled out with one 5 left over. So this is going to be 5 squared times the square root of 5 left over. There are two groups of 5 that we can pull out and one left over. One 5 left over. We can do the same thing with the x's. We know that there are 5 x's here, so there's going to be two groups of x's that we can pull out with one left over. So this is going to give us 5 squared, x squared, times the square root of 5x. Alright? But now we can simplify 5 squared, and this is a lot easier than finding 5 to the 5th. We all know what 5 squared is. 5 squared is 25. So we've got 25x squared times the square root of 5x. And there we have it. Alright, this was a long video. I am going to do another one explaining the sample problems.